Hello, I'm just going to start as people are sitting down because I have a tendency to massively run over. So, my name's Katie Barr. Do I sound stupidly loud? Or is that okay? From here I do. I'm a technical consultant with the test people, but today I'm going to talk to you about one of the simulations that I did during my PhD, which I completed last year. It was in quantum information at the University of Leeds. So I'm going to give you a quick introduction. Firstly, why you should be interested in quantum walks, which is what I'm going to show you how to simulate, and then the model itself. I'll show you how to simulate it, and you'll all be amazed at how easy it is, I hope. And then some applications directly from the simulation that I give you, and then a little bit of a wider discussion about why I had to simulate this and why physicists avoid simulation when they can. So what I'm going to show you is used by quantum computer scientists because it's universal for quantum computation. This just means it can compute anything. My personal interest in my research was exploring the power of existing quantum computational devices. What I'm going to simulate, or show you the simulation of, is done in a lab to 100 time steps. Like, we're a very, very long way off, like fully fledged quantum computers, but if we can exploit the quantum computational powers of these things, we already have them in the lab, so there's a chance that we can we can use them in a roundabout way to get better quantum computation. They also have links to other models of computation which were developed specifically to accurately model existing quantum computers. So that's a very computer sciencey reason why you should be interested. How do I go back? Oh, there we go. Okay. A much more general interest reason why you might be interested in these is the continuous time version of the walk that I'm going to do has just dropped naturally out of analyses of energy transfer in antenna complexes in photosynthetic bacteria. So we couldn't explain how this particular energy transfer from where a photon hits, if you know when you get sunburnt, that's really horrible. That energy needs to go to a reaction centre where photosynthesis takes place, otherwise it'll do loads of damage. And we couldn't explain why that happened with over 99% efficiency. We measured quantum effects in the antenna complexes this happens in, analysed the mathematical model, and the continuous time quantum walk just dropped out as the solution. So they're really widely applicable in different aspects of physics and computer science. And now I'm going to tell you what one actually is. So you've hopefully heard of the classical random walk. It's very related. It's the quantum analogue. So they both have a coin and a shift operation. If you consider the classical random walk on the line, you flip your coin, it tells you whether to go right or left. You go right or left, flip your coin again, and roughly you end up going nowhere. The expected position is 0. They can take place on arbitrary structures as well. As you can see, that graph structure there is actually an abstraction of the antenna complex. That's clearly not a line. So you can analyse them in whatever sort of geometries you like, really. They can also both be modelled in continuous and discrete time. We're going to focus on the discrete time version because it's easier to simulate, and also the continuous time is much more ripe for analytical techniques. Simulation isn't really the right way to investigate those. As I've already indicated, both the quantum and the classical versions are useful to computer scientists, physicists, and anything where you might have a bit of randomness, really. And they're easy to simulate and play about with. I've started my PhD having written 0 lines of code, and after day 1 I'd done the classical random walk. It did take significantly longer to do the quantum random walk, but luckily you can all benefit from A, knowing some Python to start off with, and B, having it given to you. So we need 4 ingredients. We need a structure to walk on, and we need an operation that moves us around the structure, and we need to model the coin flip. And this is the only complex bit, so I'm going to labour it a little bit on the next slide. And we also need an initial state, just because we need to know where we're starting, otherwise there's not much that we can reason from. So, the coin flip, if we look here, this is just an arbitrary graph, and we have 3 edges incident on node 1. Quantum mechanics is reversible. If you don't know where a probability has come into this node, you're not going to have a reversible operation. So what we do is we have what we call coin states at each node, and they simply indicate, before the coin flip, where the probability has come from, and then after the coin flip, it indicates where the probability is going to. So here we have a coin state to the right. There's obviously corresponding coin states here as well, but I wanted to keep the diagram simple. We have a coin state that says amplitudes come from the right. I should say, I'll use the word amplitude. It roughly means probability. It doesn't quite. I'll show you later how you go from amplitude to probability, but please don't lose me if I use that word. Just think probability. So, we have amplitude that's coming from the right here, and then we do our coin flip, and that's going to mix up all the amplitude from each state and tell us, finally it'll tell us what probability needs to move to the right. So the coin state then represents what's going to end up from the left coin state at node 2. And you perform your shift operation, and that's literally just a permutation. So you just swap the 2 states. So I hope that's clear so far. Right, we're going to do it over a 2D lattice, because there are still interesting results coming out of simulations of these now. So, and you probably all know how to implement a 2D lattice as well, so it should be quite easy. And we've got our up, right, down and left coin states at each node. So, just to make sure that you really understand the model, I'll show you just the first couple of steps. So I've coloured these bits in the central node to indicate that we've got probability in each coin state. So that means here, at the moment, probability could have come from any direction, and then when we flip our coin and perform our shift, it's going to go out in every direction. So we do the same thing again, and now I've made it less bright to indicate that the probability is sort of slightly lower now, because we have to preserve probability, otherwise it's not a valid physical evolution. And we have amplitude, it's gone back to the centre, but it's also gone outwards, and it will continue going outwards. It's just a choice of the simulation and initial state that I've chosen, that we don't have amplitude in this node and that node as well. So if you remember that I told you the classical random walk is expected to get you precisely nowhere, the quantum random walk propagates linearly with t. So you can actually get, in t time steps, t units away from the origin. And you can see when you do this, and when you look at the values of small simulations, you can really see the amplitude propagating outwards. Obviously, if you have a large structure and it's spreading out a lot, then the probability of measuring it at a given place is going to be very small. But there are ways that you can, clever things that you can do to tweak the initial conditions to make sure that you measure it in the place you want it to go. So now I'm going to tell you how you do that. So as I've already said, we're doing it on a 2D lattice. That's simply just a list of lists. The only important thing that you need to do is make sure that you take the right size for your simulation. So we're going to start at the origin, so that's position like 50-50, and we don't want to hit the edges, because if you hit the edges, then you need to take a little bit more care over what you're doing to make sure that you do something validly physical. So the way to avoid that is to just make your structure bigger than you're ever going to need it. And we have the values for each coin state as well. So the time step, in general, for general graphs, you have to do this with matrix multiplication. But because we have a very regular structure, we know exactly where amplitude is going to end up, so we can use that to calculate the values directly. So at the top, we've got these assignments just to make the code a bit easier to read. So at position JK0 is the left amplitude, 2 was the right, and then we've got up, down as 1 and 3. And to hopefully make it a bit clearer, I'm just going to show you how you move one bit of the amplitude around. So we're considering the amplitude at this JK position here. And we know when we do our coin flip, the amplitude from this state here is going to go to j plus 1k, this state here to j minus 1k, and the corresponding movement in the y direction. So all we have to do is apply our coin, and the coin application is this right-hand side here. So if you go back to looking at this bit, we've got these coefficients. A are all equal to a half. This is a particular choice of coin operation called the Grover coin, and you'll see very shortly why I chose to do the Grover walk. And you have to take some care about the coin operation to make sure that it's a valid quantum mechanical operation. You can't just pick any odd number for these A's. The technical term is there has to be unitary, but I can explain to you what that means if you want me to. So, literally, all we're doing is, in one step, we do the coin flip on the right, and we shift it to our new position. It's hopefully relatively simple. And you just loop over that for every position in your array for the number of time steps you want to run it for. So the last thing that we need is an initial condition. And this is where you can probably see that amplitudes and probabilities really aren't the same thing. Because you'll notice that 0.5 times 4 is not equal to 1, and we definitely need a probability probability of something happening. These days just indicate that we're using complex numbers. You don't have to use complex numbers if you don't want to. But we're starting in this initial condition because it gives you some very distinctive evolution. So if you want to check that your simulation's right, doing it against a known case that you know the answers for in advance is quite a good strategy. So in order to actually find out what positions you'd expect your walker to be found at, you need to calculate the probabilities. So here, these A's are our amplitudes, and to go from amplitude to probability, you just multiply it by its complex conjugate. You don't really have to worry what that means. The most important thing is that you just sum up the probabilities of each coin state at each position, and then you can get a nice plot of your expected position at different times. So I have a little video of it if I can make this work. Just wait 1 second. Alright. Okay, okay, that's not supposed to happen. Is there anything else that we can play this video with?
VLC installed.
Is the VLC on here? Yes. Ah, there we go. Awesome. Thank you very much. Okay, so we actually missed off the first. That's still not working. That's just the first bit. Yeah, it's. Oh, come on, video. Alright, that's not worked. It's worked perfectly on every other machine that I've tried it on, but look just dictates. But what you get basically is an oscillating peak in the centre, and you get a circle moving outwards in sort of waveforms. So if you want to see it afterwards, I can show you on my computer. Right, let's get back to the presentation. So, okay, so yeah. The reason that I chose this particular walk is because you can tweak it very, very simply to do an implementation of the fastest possible quantum search algorithm. It's called Grover's algorithm, and it's incredibly famous in the quantum information community. It's one of the big things, as well as prime number factorization, that people use as a justification for all of the investment into quantum computing. So the way that you do that, you create an n cube rather than a lattice. What you're searching for is a particular binary string. So n is the length of your binary strings, and each position represents one of those possible strings. And then you mark a state just by choosing a different coin operation, and you run it for a predetermined number of steps, and you'll find a peak at the marked state, and that runs in log n time, and you can't get faster than that. So that's why I chose this simulation. And so now that I've shown you that, I'm going to explain a little bit about why we do simulations, because some people are pretty mean about them. But there's physicists in general prefer theorems or experiments. So experiments are the hallmark of science, and I would say absolutely, like, science wouldn't be science without them. Theorems tend to be sort of beautiful, and they give you some insight as to why something is the case, as well as the result itself. Simulations don't do that. They just run a load of calculations, and you find out, oh, all these things are the same, but why? No idea. They're also really prone to human error. So the guy in the randomness talk mentioned about random numbers being periodic. In the 60s, condensed matter physicists managed to use up all their random numbers, go back to the beginning, and be really confused for several years about some interesting phenomena that they'd found. And then the simulations were rerun with better random number generators, and this bizarre behaviour just disappeared. So we had also more recent things from the 90s. I don't know why, but somebody had decided to implement their own complex numbers, and they've got a really subtle bug in there. And they got publications out of the result of this bug that they then needed to retract. I should say they are now a researcher at one of the top 10 unis in the world, so it didn't damage his career too badly. But that's a good reason, like, you need to be careful. I was lucky in my PhD, I had a mathematician that I worked with, and he would prove that my simulations were correct afterwards, so it was quite a good relationship. There's another problem that we'll never get away from is floating point accuracy. It's absolutely impossible to perfectly represent all numbers in binary. Our best physical theories, general relativity and quantum mechanics, are experimentally verified to up to 15 decimal places. Naive first pass at simulating a continuous time quantum walk, which just uses numpy's matrix exponentiation. It's accurate to 2 decimal places after 100 time steps. So I said earlier that we're doing discrete time because it's more suitable for simulation. This is one reason. The other reason is that the continuous time walk obeys the Schrödinger equation, which I hope you've heard of. The discrete time quantum walk doesn't. But we've had a good 80, 90 years of analysing the Schrödinger equation. There's a lot of mathematical techniques out there for it, so it doesn't make any sense to do work like that in simulations. But there are large reasons why you want to do simulations in science. When the discrete time quantum walk was introduced, there were no analytical results in it for 5 to 10 years. Like, it's just too difficult. If you look at a graph like this, I hope, can you actually see it? Yeah. Right. Think about like x squared or x cubed or something. Right, now think about writing down an analytical expression for that. It's just difficult. Like, luckily there are people who are anal enough to actually want to go and solve this thing. And they have, and that's why I didn't show you the quantum walk on the line, because it's analytically solved now. There's no point in doing simulations. We know absolutely everything about it. The version on the lattice isn't. So, and those proofs would never have arisen without people doing the simulations. Like, because otherwise you just pick a random thing to study. If you don't know there's an interesting result in there that needs explaining, then you're not going to bash away at it for hours and hours and hours. So that's a good reason, I would say, for running simulations. And yeah, as I said, luckily mine personally were all proven to be correct, and there's a lot of other parts of science where we still have these problems, that the maths is too difficult. I've met people working in physics, computer science and maths who are all still working on the Navier-Stokes equations. I don't know if any of you did physics degrees and remember the horrible integration things for fluid dynamics. Well, if you do, and you did, and you do, then you can probably appreciate that that's quite difficult. There's still ongoing research, and a lot of the research is about how we can get computers to efficiently do this. It's the same situation with the n-body problem. People from all over want to try and solve this, and unfortunately my boss said he was going to give me an animation of something that shows this going badly wrong, but given that my animation didn't work anyway, it's probably not too much of a problem. Condensed matter physics as well. There's once you have systems that are so vast that you can only treat them as an aggregate, but they're still very, very sensitive to changes. It becomes very difficult to tackle analytically. I know a lot of people working in semiconductors who are getting fed up with their simulations taking weeks on supercomputers, so there's still a huge amount of work going on there. Astrophysics is a bit of a different one because they can't do experiments, really. All you have is telescopes or simulations. And telescopes, they're nice, but you tend to have to be in absolutely the middle of nowhere for weeks and weeks and weeks, just up all night looking at the sky. Simulations, my friends at Leeds just run them on the Arc 1, which is one of their supercomputers, and, well, in the case of a friend of mine, got square stars out of it, though she was immensely pleased at the time just to get stars, so I think as time went on she managed to make them round. So that's everything I wanted to say about that, and I hope that you've understood a little bit about how to do that simulation, why I did it, and if you want to know any more about quantum walks or quantum information in general, I'm constantly looking for people to talk at about it, so please go for it. Thank you very much.
I think we've got time for a couple of questions if people want. No?
I'd love to, I would always ask.
Oh, one at the back.
Videos online somehow.
Oh, yeah, sure, yeah.
Thank you.
So the question was, will the videos be online?
Yeah, we'll call them online.
How long do your simulations take to run?
This one's really quick. You can run it in like seconds for 100 time steps. So it's when I ended up doing ones on the lattice towards the end of my PhD, where I had them running on 20 cores at once for a month at a time. But there, we were very interested. We'd found a property that appeared to be independent of initial conditions. And there, the reason we needed to take all that time was because we needed to test it for thousands and thousands of initial conditions, because my maths guy had tried to prove it and found it really difficult, so we were just like, we'll prove it for 10,000. And then the referees came back and said they wanted a proof anyway, so the maths guy pulled his finger out and did it for us. But in general, this is quick. As soon as you want to do anything a bit more complex or like real science in terms of being a systematic investigation, then you need a lot of computing power. Computing power was what limited me towards the end of my PhD. So.
You're doing floating point arithmetic, right?
Yeah. So I don't know much about that really. I just trust it all into numpy. So I should also say to everybody, I always put a big slide that just said numpy on it because I didn't really have the time or the knowledge to say anything about it. But when you're doing matrix multiplication, numpy does all that for you. I mentioned it earlier in terms of exponentiation of matrices. The guy in the previous talk was talking about about the linear algebra package, like that is brilliant for quantum theorists. So, sorry, that was a bit of a ramble instead of an answer to your question. But.
I mean, at the start you were talking about simulating quantum computers. I didn't understand how that fitted with this quantum random walk.
So I probably misspoke in that case. In fact, you do simulate quantum computers in this case, but are you thinking of as like simulating a particular architecture of a quantum computer rather than a simulation of a model of quantum computation? Okay. Yeah, so when I say simulating quantum computers, I mean simulating theoretical models of computation. So I came to this from a sort of automata, like quantum finite automata background. So that's what I mean. And there are quantum walk language acceptors made by me, which I would call those simulations of quantum computers, but unfortunately they're a little bit more complex than what I'd have had time to show today.
We are into the break. I imagine if Katie doesn't mind, we can carry on another minute or two, but if you're wanting coffee, you might need to dash.
Just one question then to wrap it up. I won't keep you long. So in a sense with quantum biology, I think I read this in New Scientist, you're saying that photosynthesis is a computational process? Life is computation?
So I really shy away from grand claims like that because you can interpret anything as a computation. So all that exciton is doing, in one sense, is computing the most energetically favourable trajectory for it. Now, that's just time evolution. Whether it's a computation or not is up to, well, my supervisor actually did some work on this and came up with the idea that something's only a computer if you've built it to compute things. If it's just evolving naturally and you're calling it a computation, then I'm not sure if that's valid. But you can, it's open to interpretation. No.
Thank you very much.
Thank you.
Thank you very much.